Welcome to how to use the Sonus PD. Partial discharge is generally accepted as the predominant cause of long-term degradation and eventual failure of electrical insulation. As a result, its detection has become an important part of testing of all types of electrical assets. In addition, partial discharge activity can be tested for or monitored on in-service equipment to warn against pending insulation failure. The Sonus PD Pro and Sonus PD X are partial discharge detection devices offered by IRISS LLC. These multifunctional devices have the capability to detect partial discharge as well as ultrasonic emissions in electrical assets. With 4 modes of operation, the Sonus PD Pro and Sonus PD X allows the inspector to test transient earth voltage known as TEV, high frequency current transform known as HFCT mode, and ultra high frequency known as UHF in addition to the ultrasound. They can be used to find 6 partial discharge events. While the acoustic emission, referred to as AE, better known as ultrasound, can pick up 6 partial discharge events, it can also detect dirty power and loose connection events. The Sonus PD Pro and Sonus PD X have the unique ability to synchronize with the phase of the power supply that is present in the substation. This feature ensures that the unit is consistently looking for the most accurate phase from the power supply. The Sonus PD Pro and Sonus PD X will consistently adjust to ensure that it is synchronized with the truest form of the phase occurring in that room. This helps the inspector to ensure that they are properly testing and always receiving the best quality of signal strength from the transient earth voltage that is being discharged in the metal cladded gear. In this course, we'll go over the introduction to the Sonus PD Pro and Sonus PD X. We'll discuss what is partial discharge. We'll talk about effects and consequences, and we'll give you some examples. We'll also discuss where and how the PD occurs, some features and benefits of the Sonus PD Pro and Sonus PD X, the difference between TEV, AE, HFCT, and UHF, the PD signals, analysis and detection, how to use the Sonus PD Pro and PD X, the Sonus PD app, and also we'll give a brief introduction into the Sonus View app and desktop software. So, what is a partial discharge, you may ask? Well, it's an electrical discharge that does not completely bridge the space between 2 conducting electrodes, and 80% of failures in switchgears are directly related to partial discharge events. These partial discharge events can be caused by gas-filled voids in solid insulation, which are bubbles in the jacketing of the cable, which can lead to failure over time. These voids can be caused by substandard cabling manufacturing practices or environmental exposure. Partial discharge may be found in liquid-filled transformers where the paper insulation starts to degrade with exposure to high heat levels. This will lead to the oil losing its insulation value and the degradation of the cellulose paper becomes more rampant. This produces bubbles in the oil, which allows the conduction of current inside of the equipment, which in turn will show up as TEV, AE, HFCT, or UHF indications. For too long, the electrical inspection has been relegated to an annual inspection due to the fact that they were usually carried out on open and energized equipment. Now with the ease of testing devices to not only determine the decibel value in TEV, AE, UHF, and picocoulomb in HFCT, but the addition of phase-resolved partial discharge known as PRPD Live and PRPD Persist modes allows the inspector to quickly see the pulse cycle that will be present when one of the 6 partial discharge events are detected. Partial discharge can occur around the connections and insulators on transmission lines or in a substation. Chemically, the discharged energy breaks down the chemical bond of the oxygen atom, which in turn turns it into nitrogen oxide. This will leave a white powdery substance around the anomaly that, if exposed to moisture, turns into nitric acid. Partial discharge activity inside metal-clad high-voltage gear induces small voltage impulses called TEV, or transient earth voltage, on the surface of the metal panels. The TEV travels around the surface to the outside of the switchgear, where they can be detected or picked up externally by using a PD detection device like the Sonus PD Pro and Sonus PD X. There are 6 types of partial discharge that can be detected using TEV or ASU devices. Infrared will pick up 2 of these, which in turn helps to prove the exact fault condition occurring inside the asset by process of elimination and correlation. We discussed already the ionized bubbles occurring in oil-filled transformers. We also covered insulation voids and what they can do. We discussed corona. Now let's discuss treeing. Treeing occurs as the current from the fault condition begins to migrate out and away from the source across a normally insulated surface without bridging the gap. This will be detectable using TEV and ASU devices. Tracking occurs when a continuous conductive path has been established across an insulative surface. This path allows for the current to creep across the surface in an attempt to find a path to ground. This will produce TEV, ASU, and infrared indications. Arcing occurs when electrical current jumps from one point to another. This can happen with or without treeing or tracking prior to the event. This too will also be detectable using TEV, ASU, and infrared technology. Sound analysis can also be a key determining cause of the exact fault condition that's present when looking for these 6 partial discharge events. They will each have a distinct pattern when viewed in software, and in a time signal analysis versus the frequency spectrum. These distinct images in conjunction with the PRPD screens and level modes allow the inspector the ability to make a decision about what steps to take next in the asset's health. Defects on the surface of a high voltage insulator are prone to phenomena known as treeing and tracking. These cause carbon deposits to build up over time, ultimately leading to flashover and insulation failure. The partial discharge detection device is highly sensitive to TEV and ultrasonic emissions produced by these events and can find the incipient stages of partial discharge events before a phase-to-phase and phase-to-ground event can occur. As the insulation value around the anomaly breaks down, the magnitude and number of pulses increases dramatically, and over a 6-month period, this could easily double and lead to faster end of useful life for the gear. The use of the comparison method can quickly identify any outliers that need further investigation. When using the comparison method, the inspector can not only compare similar equipment, but the same asset over time. In order to do this, the humidity, temperature, load, and voltage all need to be documented in addition to decibel values. PRPD results in sound waves at the time of testing will also be beneficial. Trending of the assets can be also established with enough historical data, and analysis of the PD cycles, decibels, and sound waves is critical. This information will allow the program to make an even more effective determination of why or when there may be an increase in the breakdown of the voltage. If these assets are left untested, the emissions will go undetected and will lead to a catastrophic failure. Partial discharge, known as PD, as defined by IEC 60270, are localized dielectric discharges in a partial area of a solid or liquid electrical dielectric insulation system under high voltage field stress. Partial discharges in a transformer deteriorate its insulation and can lead to failure of the transformer. So what are the consequences of PD? Well, how does a failure attribute to partial discharge cost at a site? Just ask Delta Airline how much the failure of a high voltage switchgear cost them in Atlanta in 2016. Since it probably won't answer your call, it was estimated that the cost was $50 million for the 11 hours they were down. That was over 1,400 flights that were canceled. I was traveling that day, and even though I wasn't directly affected, Delta even sent everybody flying that day an additional 25,000 Skyline miles as an apology for the issues that it may have caused their travel on that day. Think about that added cost. The consequences and risks of partial discharge are pretty wide and varied. Partial discharge is most likely to occur during switching. It is essential to test before the switching process is engaged. If partial discharge is present, manually switching must not take place. Consult your company's policy and procedures for whether remote switching should take place in this situation. The Sonus PD has the unique ability to synchronize with the phase of the power supply that is present in the substation room. This feature ensures that the unit is consistently looking for the most accurate phase from the power supply. The Sonus PD will consistently adjust to ensure that it has synchronized with the truest form of the phase occurring in that room. This helps the inspector to ensure that they are properly testing and always receiving the best quality of the signal strength from the transient earth voltage that is being discharged in the metal-clad gear, or the airborne ultrasound that could be present from these same events, and even HFCT and UHF anomalies that will present with these 6 known partial discharges. Arc flashes may appear to occur suddenly, but in reality, they start off as a small partial discharge event and can quickly escalate when atmospheric conditions have a high humidity value or contamination value. This can lead to the events we're about to see here. Partial discharge occurs anywhere there is a junction, such as a termination, a spout, bus bar connection, or electrically stressed insulation. Up to 80% of switchgear related failures are suspected to be related to partial discharge events, which allows for a phase-to-phase or phase-to-ground event to occur, leading to an arc flash. So with 70 to 80% of electrical failures in medium and high voltage equipment being attributed to partial discharge in insulating materials, this simple fact should be enough to sell a company on the ROI of the Sonus PD product line's ability for early detection of TEV and ultrasonic emissions that would indicate fault conditions are present. So what are the effects of PD? Partial discharges are individual discharges of low energy that are very localized and can be very, very repetitive. The damage is caused either through mechanical, which is in ionic bombardment, thermal, which is the local heating at the discharge site, or chemical, which is discharge energy breaking down chemical bonds. The Sonus PD has several benefits. Some of them are very, very easy to hear, such as ultrasound. Non-electrical noise is shifted to a -6 decibel in TEV, AE, and UHF mode. It's easy to see the display screens, easy to connect to the HFCT and UHF transducers. It's light and easy to use, and it's easy to connect to the app that's available for the Sonus PD Pro. It's easy to use its interface for the database as well in both the Microsoft platform or the cloud-based software. The Sonus PD's built-in noise rejection gives the inspector instant confirmation of the presence of noise versus TEV, ultrasound, HFCT, and UHF. This allows for quick diagnosis of a potential fault condition inside the equipment. The unit will automatically shift any antagonistic noise values to the right of the screen and list the value, so the inspector feels confident the value on the screen is an actual partial discharge event versus antagonistic noise. With many electrical assets being stretched past their original design life, lack of attention to these assets can come back to bite you if you're not testing them. With Sonus PD, there is no service interruptions, and it can quickly be deployed to perform crucial surveys to prevent unscheduled downtime. The Sonus PD Pro can be connected to the Sonus PD app. This allows the inspector to easily see what the device is detecting in several screens. IRISS is now proud to offer 3 different models of PD detection. First, with the Sonus PD Alert, a site can continuously monitor their hard-to-reach electrical assets with continuous monitoring, or use a handheld with routine routes on the assets. An improved noise rejection filter has been included in the new firmware, the Sonus PD Pro and the Sonus PDX, to allow the device to shift any non-electrical anomalies to a value of -6 decibels, letting the inspector know that the presence of the sound is not electrical or transient earth voltage in nature. IRISS now offers 2 models of the Sonus PD. One is the Sonus PDX. This model will allow the user to inspect for TEV, ultrasound, and with the additional transducers, they can then detect HFCT and UHF. The Sonus PD Pro offers the same exact features with the addition of the Bluetooth connectivity, which allows you to connect your Sonus PD Pro to the phone app. It also allows you to save your data and transfer it to either the Microsoft platform or a cloud-based software. Partial discharge activity inside metal-clad high-voltage assets induces a small voltage impulse called Transient Earth Voltage along the surface of the metal panels. TEV travels around the surface to the outside of the switchgear, where they can be picked up externally using the Sonus PD Pro and Sonus PDX. Defects on the surface of a high-voltage insulator are prone to a phenomenon known as surface tracking. Tracking causes carbon deposits that build up over time, ultimately leading to flashover and insulation failure. The Sonus PD Pro and Sonus PDX detectors are highly sensitive to the ultrasonic emissions produced by tracking and enables the early detection before insulation failure. With the addition of the HFCT clamp and the UHF transducer, the inspectors can test other assets that were once untested when using ultrasound or TEV detection equipment for the location of partial discharge events. With each mode offering 3 views for the inspector to review the information received with the Sonus PD Pro and Sonus PDX devices, the inspector can switch from a spot test, which will display the decibels being received in TEV, ultrasound, and UHF mode, and in picocoulombs while operating in the HFCT mode. These screens will allow the inspector to see the intensity of the anomalies present in the asset or being emitted from the cabinet while testing energized gear. These screens quickly allow the operator to identify the exact source of the anomaly and run a comparison method between multiple cabinets to see which one has a higher intensity level. This allows the inspector to quickly target an area of concern and make a call on the asset's health. The second screen is the live phase result partial discharge, or better known as PRPD live measurement screen. This screen will display each partial discharge as it occurs, giving the user a defined block of amplitude as each of the occurrences discharges. The third screen is the data that was accumulated in the first and second screens. This is the PRPD persist screen, which will display all the partial discharge events in a spectrogram that will appear to have rounded tops indicating the partial discharge events are occurring, and what their total amplitude over the entire duration of the data that was collected. These clearly defined humps are the telltale signs of the presence of transient earth voltage or a partial discharge event. The Sonus PD Pro is the PD detector that is an ideal tool for personal safety, routine substation testing, and first-line PD detection. Its fast testing of the entire substation allows for the testing of AIS and GIS as well as cabling. The PD level detection with TEV, Ultrasound, HFCT, and UHF gives the inspector the confidence that they're able to determine what is occurring. The phase resolved PD and TEV, AE, HFC, and UHF also allows the inspector another view and dimension of what is occurring on their screen. Electrical noise interference again is detected and separated from the actual display of the intensity of the anomaly. In use along with any smart device app for data saving and data synchronization, which allows the user to then open up the data that was acquired in the field and review it either on a Microsoft platform or cloud-based software. The kit includes a PD detector unit, headphones, a PDFT function tester, a USB charger, and hard-wearing Pelly case. With the Bluetooth feature, the inspector can instantly change the mode of operation and the screen views with the phone app. They can also view data in a scatter plot to look for the indication of partial discharge events. And again, this data can be stored and retrieved either using Microsoft or cloud-based software. The Sonus PD-X offers all the same modes of operation as the Sonus PD Pro, but without the Bluetooth feature. This means that the app cannot be paired to the device, which affords secure sites the same performance abilities to test for partial discharge events without having to worry about the security risk of a Bluetooth-enabled device. The differences between TEV versus AE, better known as ultrasound, HFCT, and UHF. TEV stands for Transient Earth Voltage. TEV is an electromagnetic wave that falls in the radio spectrum of the electromagnetic wave spectrum. TEV is a voltage-induced spike that transfers to the cabinet's housing as a partial discharge attempts to find a path to ground. TEV occurs as these spikes emit out from the source, creating the current spikes in the conductor and earthen metal surrounding those conductors. This generates a wide range of electromagnetic waves spanning from the kilohertz through the megahertz range. As the voltage spikes and incident waves strike the earthen metal of the cabinet, they produce a detectable TEV at a range of 0 to 200 megahertz. They travel at different frequencies through these mediums, and the TEV will potentially travel at a further distance than ultrasound since the distance between its peaks can be much closer together than those in the ultrasonic range. This is why TEV can be heard in adjoining cabinets versus ultrasound, which is easily impeded, diffracted, attenuated, or reflected away from the ultrasound testing device. The Sonus PD can detect decibels from -6 to 60. Dual-colored LEDs indicate the intensity level using green, yellow, and red lights. When operating in TEV mode, values between 20 to 29 signals a medium level of partial discharge event is occurring. 30 decibels and higher indicates a high level of partial discharges occurring in the TEV realm. Non-TEV anomalies are shifted and displayed as noise on the screen. Transient Earth Voltages, better known as TEV, was first discovered in the 1970s by Dr. John Reeves, who established that TEV signals are directly proportional to the condition of the insulation for all switchgear of the same type measured at the same point. TEV readings are measured in decibel microvolts. TEV pulses are full of high-frequency components, and hence the earthen metalworks presents a considerable impedance to ground, and therefore voltage spikes are generated. These will stay on the inner surfaces of the surrounding metalworks to a depth of approximately 0.5 micrometer in mild steel at a frequency of 100 megahertz and loop around to the outer surface wherever there is an electrical discontinuity in the metalworks. There is a secondary effect whereby electromagnetic waves generated by the partial discharge also generate TEV on the surrounding metalworks as the surrounding metalworks begins to act like an antenna. TEV anomalies are a very convenient phenomenon for measuring and detecting partial discharge as they can be detected without making an electrical connection or removing any panels. While this method may be useful to detect some issues in switchgear and surface tracking on internal components, the sensitivity is not likely to be sufficient to detect issues within solid dielectric cables. The difference between AE, TEV, HFCT, and UHF. AE is referred to as airborne emissions in the ultrasound range. AE is actually an airborne structure-borne ultrasound, better known as ASU, discharge from the anomaly that can be transmitted through the air or along the structure's housing. ASU is an electromagnetic wave that falls in the radio spectrum of electromagnetic waves. This generates an ultrasound signal in the 20 kHz up to 100 kHz range, which can be picked up with an airborne transducer as the sound travels through the air around the anomaly. Structure-borne transducers can detect the anomaly's emission as the once airborne sound interacts with the secondary medium of the electrical gear and now produces a shear, plate, and surface wave that travels along the panel. They travel at different frequencies through the mediums, and the ASU will not travel as far as the TEV, since the distance between its peaks can be further apart than those in the TEV range. This is why ASU can be heard through gaps and holes in the cabinets, but they can still be easily impeded, diffracted, attenuated, or reflected away from the ultrasound testing device. What do the decibels in the AE mode indicate? When operating in AE mode, values between 0 to 30 decibels indicate the presence of a partial discharge event in the ultrasound realm. Decibels, however, are not the best indication of failure. The best way is to record and analyze the occurrences that are found. The Sonus View app and Sonus View desktop can be used to determine the exact fault condition that has been found in electrical gear. So ultrasound emissions can be detected using the dedicated piezoelectronic transducer for monitoring for corona, treeing, tracking, arcing, delamination and windings, and many other electrical faults that can occur inside these assets. Typically, these transducers are centered at 40 kHz, and it is a line of sight. If you cannot see the target, you will have a hard time acquiring the sound and detecting its exact source. Ultrasonic measurements rely on the fact that partial discharge will emit sound waves. The frequency for the emission is white noise in nature and therefore produces ultrasonic structure waves through the solid, liquid-filled electrical components or through air. Using an airborne structure-borne ultrasound sensor on the exterior of the item under examination, internal partial discharge can be detected and located with the sensor if it's placed closest to the source. If you add the VPDS from IRISS, you can actually get a reliable test point with one single location instead of having to trace the seams. This will give you a repeatable test point for the detection of ultrasonic emissions and TEV occurrence inside the electrical gear. The difference between HFCT, TEV, AE, and UHF. HFCT stands for High Frequency Current Transformer. HFCT is an electromagnetic wave that falls in the radio spectrum. It is generated by a localized dielectric breakdowns in a bandwidth of 60 kHz to 70 MHz as the anomaly propagates away from the source of the emission. The HFCT clamp can detect these events and display the signal on one of three screens on the handheld unit that's used to detect these electromagnetic pulses created by these anomalies. Whenever partial discharge is initiated, high-frequency transient earth voltage current pulses will appear and persist for nanoseconds to microseconds, then disappear and reappear repeatedly. What do the picocoulombs in HFCT indicate? The picocoulomb is an SI unit used to measure electrostatic charge. In the HFCT mode, the unit can be used to couple to an HFCT clamp to detect the presence of a partial discharge event. If a unit is receiving less than 99 picocoulombs, this anomaly would be rated low on the alert action report. Between 100 to 499 picocoulombs, this would be a medium alert on the action report, and 500 picocoulombs or greater would be a high alert for the action report. PD pulses are easy to measure using the Sonus PD Pro or the Sonus PDX while in the HFCT mode. The HFCT clamp is a high-frequency current transducer which is clamped around the ground of the component being tested. The The severity of the PD is measured by measuring the burst of intervals between the end of a burst and the beginning of the next burst. As the insulation breakdown worsens, the burst interval will shorten due to the breakdown happening at lower voltages. This burst interval will continue to shorten until a critical 2 millisecond point is reached. At this 2 millisecond point, the discharge is very close to the zero crossing and will fail with a full-blown discharge and major failure. The HFCT mode needs to be used since there is only a small magnitude and short duration of these PD events. The HFCT method is done while the component being tested stays energized and loaded. Another method of measuring these currents is to put a small current measuring resistor in series with the sample and then view the generated voltage on an oscilloscope via matched coaxial cable. The difference between UHF versus TEV, AE, and HFCT. UHF stands for ultra high frequency. UHF is an electromagnetic wave that falls in the radio spectrum. UHF is generated by localized dielectric breakdowns in a bandwidth of 200 MHz to 2.5 GHz as they propagate away from the source of the emission. Radio waves with frequencies above the UHF band fall into the super high frequency, better known as SHF, or microwave frequency range. Lower frequency signals fall into the VHF, or very high frequency, or lower bands. UHF radio waves propagate mainly by line of sight. They are blocked by hills and large buildings, although the transmission through building walls is strong enough for indoor reception. They are used for television broadcasting, cell phones, satellite communications including GPS, personal radio services including Wi-Fi and Bluetooth, walkie-talkies, cordless phones, and numerous other applications. So what do the decibel values in UHF indicate? Well, if we use them to detect partial discharge in electrical high voltage cable terminations, better known as GIS or gas insulated switchgear, we would mount the UHF sensor against the insulating barrier spacers that separate the components of the high voltage assets. This makes them great at detecting the PD inside of the GIS and other similar setups. A low alarm would be considered anything below 39 decibels. A medium alarm value would be 40 to 54 decibels. And a high alarm value would be 54 decibels and higher. UHF testing is effective at detecting PD in GIS and other similar setups, so for on-site PD detection, the ultra-high frequency mode has been employed in the field and showed its effectiveness as a detection technique. The main advantage of UHF method is its immunity to external electromagnetic interference with a high signal-to-noise ratio, which is necessary for on-site monitoring. Considering the detection process, sensors play a critical role in capturing signal from PD sources and transmitting them into the UHF sensors. UHF signals escape through gaskets and spacers. The UHF sensor should be installed at this point. Recommended termination in CB areas, but it can also be used elsewhere. Typically, the partial discharges will be in a range of 500 MHz to 1.5 GHz. This device is intrinsically rated or EX rated. Utilizing the Sonus PD Pro or Sonus PDX with the UHF sensor will allow the inspector to detect partial discharge in electrical high voltage cable terminations, GIS or gas insulated switchgear, GIL, gas insulated transmission lines, and GIT, gas insulated transformers. The sensor picks up signal in the UHF range by mounting it against the insulating barrier spacers that separate components of the electrical high voltage asset. Now let's go through how to actually use the Sonus PD Pro or Sonus PDX. First, you'll need to remove the device from the case, as well as the PDFT tester. Next, power your Sonus PD Pro or Sonus PDX and the PDFT and place the back of it against the capacitive coupler. Switch from TEV to AE mode by pressing the M button on your Sonus PD unit and place the PDFT feet up against the front of the Sonus PD unit's embedded ultrasound transducer. Next, you can take the Sonus PD unit out to the field and place the PDFT on a metal panel to simulate TEV. Move your device around and look for the decibel value on the TEV mode to increase as you get closer to your PDFT unit. Again, switch from TEV to AE mode by pressing the M button on your unit and listen for the PDFT in the acoustic emission range, better known as ultrasound. The Sonus PD units can even be purchased with an optional parabolic dish, part number PD55, and with a cable ADC-PD55-PD for airborne ultrasound testing of overhead components from a safe distance. Now let's pair the device with the Sonus PD app on your Android phone. Start by opening the app on your phone and then click on the Detect device. The Sonus PDs will display on a list of units available to link up to. Choose the unit serial number by tapping the screen, then press Connect. Enter the default PIN of 1, 2, 3, 4 and click OK. Once you've connected successfully, the following screen will appear, which shows you what version of software the app is currently running, the serial number of the unit you're using, what main frequency you're utilizing, whether it's 50 or 60 Hertz, and you would just need to tap the Acquire tab to enter active screens. This screen will even allow you to update the firmware very easily by simply clicking the FW upgrade. Then hit the upgrade button to update the software firmware is available. The next screen will allow you to name the substation, panel, or assets and the number of readings you plan to test. When you're ready to start, click the Go tab. This will launch you to the reading screen, where you'll be able to see either the live mode in TEV, AE, HFCT, or UHF. Once you've selected your mode, the live PRPD mode will open up and start to display the activity of the anomaly. As the unit synchronizes with the power cycle phase in the asset being tested, it will start to display a scatter plot. In the interpretation of the site's sound waves, it is important to understand the importance of the sound quality for diagnosis. This includes understanding the difference in sound wave patterns of corona, treeing, tracking, arcing, dirty power, loose windings, mechanical looseness, delamination of windings, 60 cycle hum, 50 cycle hum, stray voltage, outer race, inner race faults, cage faults, ball pass faults, back pressure issues, bad slow speed bearings, steam trap discharge rate, and normal operating sounds. For those that want to be able to record sound waves, it will require the additional purchase of the Sonus View Pro desktop software, which comes with the free phone app, which works both on iPhone platforms and Android. The first step to recording would be to take the PH split cable, place it into the headphone jack on the Sonus PD unit that you have. Then you can plug your headphones into one of the splitters jacks, and the other one you'll use the cable XT phone cable to run to your phone that you are using to record on the app. Then go to our How to Use the Sonus View app to follow the steps on how to record a sound wave, name it, save it, and send it via one of 8 different methods back to a tablet or to a laptop to analyze. To transfer files to your laptop or desktop when tethered, simply insert your USB cable into the device and download the files directly from the phone. Look in your Explorer for the tethered device. Enter the DCMI files to retrieve the sound waves from your device. And then we recommend that you create a sound wave folder on your laptop or computer and save the files under a subfolder with the company name. Once in the folder, the sound waves can then be accessed by the Sonus View Pro desktop software. So now let's discuss how to interpret the signal. With the Sonus app, the user can look for repetitive harmonic values that will indicate that there is an ultrasonic anomaly present that should be looked into further. These patterns can indicate such things as delamination of windings, loose connections, dirty power, arcing, treeing, tracking, or corona, just to name a few. With 3 options for viewing the signal, the user can choose the screens they like best. Time signal is my preferred method of displaying the values being seen on the screen, but the display scaling compares positive and negative amplitudes in millivolts versus time. In frequency spectrum, the display scaling compares the frequency of how often an event is occurring and its decibels at those different frequency values. In a combined screen of time signal and frequency spectrum, both screens are displayed simultaneously. This makes the screens much smaller and harder to see. The recommendations from IRISS are to choose one of the 2 listed above as your single screen to view. The phone can be tilted when using the Sonus app, but it is best to only have one of these options open again and use it in landscape so the values can be seen more clearly. There is no harmonic marking capability on the phone app. This prevents the user from being able to actually mark harmonics, only to see them. The Sonus app is the first step in identifying if there's an issue present and warrants further investigation using the Sonus View Pro desktop.